So as we dig deeper into trying to understand how the atmosphere can produce such incredible expressions of severe weather, we're now starting to talk about thunderstorms. So in this video lecture, we're going to be talking about the ingredients that have to come together to make severe thunderstorms. Now, as we get started, we're going to break this down pretty simply. We're going to talk about the first ingredient quite a bit because it's one of the most complicated to understand. But once we put it all together, you will understand how the atmosphere is able to make these three main types of thunderstorms. So these are what we're going to be learning about in the next several lectures. In the bottom panel, let's start there. I got a picture of what we call an ordinary thunderstorm. It's one that's non-severe. We're going to talk about how that thunderstorm forms and why air rises so violently inside of it. We're then going to break our thunderstorm types up into two main types. First, on the left, we'll talk about the squall line. We'll call this the mesoscale convective system, or MCS, in our class. These are long lines of thunderstorms that are responsible for producing a lot of straight line wind damage, but they can also produce flooding rains. They can even produce brief tornadoes and also some hail, but they're most commonly known for their ability to produce strong straight line winds. And then we'll finish up by learning about that storm in the upper right-hand corner. You've seen this radar image before. This is the supercell thunderstorm that hit Greensburg, Kansas. So when we get into our lectures on tornadoes, we're going to focus a lot on this type of thunderstorm. Pound for pound, that storm in the upper right-hand corner, the supercell, is the most violent expression of weather on Earth. And so here we go. What are the ingredients that have to come together to make this? Now, as we get started, I'm going to give you a quick overview of thunderstorms. The generic name that we give a thunderstorm is a cumulonimbus cloud. And cumulonimbus just means a vertically developing heap of clouds. You see, there are two common cloud types in atmospheric sciences. If we just had to break it down into two big types, we have the cumuliform clouds, those that develop vertically. We have the stratiform clouds, those that develop horizontally. So, the cumulonimbus cloud is a big vertically developing thunderstorm cloud that contains, as you can see, our lightning and thunder. Now, thunderstorm season in the United States, and practically all of the northern hemisphere, runs from March to September, and that's because the four ingredients we're about to discuss come together most commonly during those months. Now, that map that you see there in the upper right-hand corner shows you the number of days per year with thunderstorm activity. So clearly in the United States, Florida and the Gulf Coast is kind of the hot spot. And that particular region can have thunderstorms any time of the year because they remain warm enough, have enough moisture in the atmosphere to continually make those thunderstorms. So in some spots in Florida, 100 days a year of thunderstorm activity. Where I'm recording this lecture here in Champaign, Illinois, we typically have about 45 days per year. There's a secondary hotspot, which you see right over here in parts of Colorado and New Mexico. And the reason for that is that this particular area, sitting right along the front range of the Rocky Mountains, has kind of a permanent region where we have lift in the atmosphere, the mountains. And as a consequence, there's a lot of thunderstorm activity there throughout the year. But remember, March to September, that's our typical thunderstorm season. And to help you remember that, look at the graph that's just below the picture of the United States. You see, I've shaded in for you here March to September. Really, that time period is characterized by an increased number of severe weather events. So each bar that you see in this graph is a report or series of reports to the Storm Prediction Center showing you how many different severe weather events happen that day. So sometimes we have well over 500 reports. In fact, the busiest day on record had over 1,400 reports of severe weather. And we'll talk about that later on this semester. So you can kind of see while you can have severe weather events outside of the shaded area, which again goes from March to September, really the bulk of our severe weather is going to be happening in those months. Now, big things to remember. 200 plus deaths per year caused by severe weather. So I'm talking here about deaths from tornadoes, deaths from flash flooding, hail, strong straight line winds. Those are the main categories I'm using. Property damage can be well over $15 billion. And a lot of that comes from agricultural losses. So we're not only hurting buildings and homes, but we're also blowing down crops or destroying them with hail. But it's interesting. We kind of have a love-hate relationship with thunderstorms. The love part of them is this. They deliver an enormous amount of water to the soil, and we need this. We need the thunderstorms to regularly interact with our breadbasket, the Great Plains, the Midwest, that region in the country to give it the rains that we need in order to produce the food that we produce there. By the same token, in the southeast, where we grow a lot of cotton and peanuts and a whole bunch of other crops, including citrus and other things, we need to have the regular thunderstorm activity to provide the moisture necessary to get those crops to grow. I'm going to tell you something. See that little picture I took in the bottom there, that bottom panel? There was just a couple of pop-up thunderstorms kind of sitting off in the distance, and I was in Urbana, Illinois when I took these pictures. Those storms are tiny, yet in each one, there are billions, and I'm not exaggerating, billions of gallons of water. You see, we have to understand how in the world can the atmosphere support billions of gallons of water just floating above our heads. And we're going to try to figure that out as we dig into this first ingredient. So here's some questions that we're going to have to try to answer, okay? Why do thunderstorm clouds do what you see here? One of my students, Adam Springer, took this beautiful time lapse of some storms on the Great Plains. Look, the air is rapidly ascending very, very quickly. Yet it's full, absolutely full of liquid water and ice and snow and all sorts of other stuff. Yet how does it rise so rapidly in the troposphere, and why is it able to support so much weight, the weight of all that water? Well, the answer to that question lies in this time lapse. Check it out. One of my favorite videos here. Time lapse of a hot air balloon day. Okay, we can see these balloons rapidly being filled with hot air, and all of a sudden they become buoyant and they take off in the atmosphere. If you understand that one concept, if you understand this principle of buoyancy, you will get the most complicated ingredient and honestly one of the most complicated lectures that I'm going to give you this semester. So sit back, tuck in, we're going to dig into this. This is the most complicated stuff we're going to dig into this semester. So our first ingredient, the very first thing we're going to have to try to understand is this concept of stability. Stability is resistance to change. And what I'm showing here is a picture of what are called the Devil's Marbles, which is in Australia. Now look at these two large boulders sitting on top of these other boulders here in Australia. I want you to think about this. If you walked up and applied a force to this boulder, let's push on it really hard in that direction, okay? If you were to do that, this thing would not move. Even if you came up here with like, a bulldozer and started pushing on this, it's going to take an enormous amount of effort to get this particular boulder to move. And that's because it is very resistant to change. Now on the flip side, if you come over to this boulder and push on it with the same force, it will probably, well, accelerate or fall off and into the ground. You see, that's a very, very important lesson for us to understand because we're going to be talking about how we can get air to move vertically in the atmosphere. And when it comes to stability, we want the atmosphere to be in an unstable situation to make thunderstorms. Remember that boulder number 1 right over here is very stable. We push on it, it doesn't move. But boulder number 2, which is this one, any force applied to it, and it will easily rock or fall off of this very small little area on which it is sitting right in through here. So that's what we're going to try to understand as we dig into this concept of stability, the resistance to change, okay? So here we go. To help you understand this, I need to introduce a new concept here. It's a concept of what we call parcel theory. Now, what is a parcel? I got it there in red. It's a blob of air. You can identify this blob of air as it moves throughout the atmosphere. Hold out your hands and just grab a blob of air. There you go. You're holding a parcel. Or think about the parcel of air in the room that you're currently sitting in. The air in the room, that can be considered a parcel. Or maybe you're watching this video outside at a park. Well, the air sitting over the top of the park, you can call that a parcel. We're just identifying a chunk of air. Now, anything that's outside of that chunk of air, we're going to call the environment. Maybe an easy way to think about this is to think about it like a balloon, right? A balloon holds air on its inside. Think about that balloon as the parcel, and everything on the outside of it as the environment in which the parcel is sitting. Turns out that just like the hot air balloon video we watched, the atmosphere, especially with massive supercells like this, behave in a very similar way. What makes a hot air balloon go up? Well, the hot air. The hot air is less dense than the cold air around it. Well, the hot air is in the parcel. The cold air around it is the environment. And here's the neat thing. Just like with the hot air balloon, the canvas serves as a barrier, preventing the hot air from the inside mixing with the air on the outside. The atmosphere, see that massive thunderstorm there? That's one giant parcel. And it is not mixing very well at all with its environment. And therefore, if I can get this parcel of air to be warmer than the surrounding environment, which is all this, it will ascend. And the reason why this works is the whole process is behaving adiabatically. Now, that's a new term for a lot of you. For all of us today, I just want you to think that adiabatic means no mixing of the air in the parcel with its environment. That's why clouds have these really well-defined hard edges on them, like you can see here. You have the thunderstorm cloud, which is the parcel, and its environment that surrounds it. So what's the key idea? Compare inside temperature to outside temperature. Compare the temperature inside the parcel to the temperature of its environment. And that is a tricky and complex concept to understand. So we're going to spend most of this video lecture trying to digest just that one idea. So let's dig into this. First thing I want to talk about is how the air can cool and warm. We're going to be talking about two big concepts. One, expansional cooling, and the other, compressional warming. Now, it's the middle of summer when I'm recording this lecture, and I just took my kids to swim team practice. And when we go out for swim team practice, I spray on them sunscreen. They have pretty fair skin, and as a result, they'll burn if I don't put sunscreen on them. Now, my kids hate this. Well, they love the feeling of sunscreen because sunscreen reminds them of summer, but when I spray the sunscreen on them, it's very, very cold. Now, why is it cold? Well, inside of the bottle, we have compressed liquid we have liquid and compressed gas. And the mixture of which, when we push on the nozzle, basically allows it to rapidly expand out of that nozzle. And as it expands, that expansion process, well, it's cold. And when it arrives on my kid's skin, well, there's two processes working here, the expansional cooling and the evaporative cooling that basically makes the spray hit your skin quite cold. Now, if you've never done this, maybe you've sprayed your hair with hairspray. Have you noticed that when you do that, the hairspray falls on your head, it's cold, and the can in which you hold when the hairspray evacuates it, it gets cool as well? You see, as air is allowed to expand in the atmosphere, it does work on its environment. It expands against the environment, and that effort reduces its temperature. So we have this process called expansional cooling. Now let's think about the opposite of this, compressional warming. Now I'm a gearhead. I've owned 27 different cars in my life, and I love to work on them. I think that the automobile is just the coolest thing ever invented. So if you wouldn't mind, let me take you through a little bit of a trip of understanding here about car internal combustion engines. And it all revolves around this question. Have you ever wondered why you have multiple options when you go to the gas station to fill your gas tank up with different octane gases? I mean, why do you have, well, like we have here in Illinois, 87 octane or 91 octane or 93 octane? What the heck is the difference? Well, the difference has everything to do with your engine's ability to compress a mixture of gasoline and air. You see, you're watching here a 4-stroke engine. And stroke number 2, which you'll see here in a moment, right here is a compressional stroke. In other words, we let all of the gas mixture in with basically point number 1. The piston then goes up and compresses that gas in bullet point number 2. And then there's a spark which causes it to explode. The piston rushes down in point number 3. And then an exhaust valve opens up in number 4 and lets all the exhaust out. That's it. That's an internal combustion engine. Now, why do we have different choices of gasoline? Well, high-performance engines are high-compression engines. And when you compress a mixture of gases, it has to heat. You ever pumped up a bicycle tire? You know that when you hold the cylinder in which the plunger is going up and down in, the cylinder with time gets warm. That's because you're compressing gas in there. Now, when you compress the gasoline and air mixture inside your engine, it warms up rapidly. And well, you don't want it to get warm enough to where it automatically ignites before the spark plug, which you'll see here again at the end of stroke 2 right there, says to ignite. So therefore, higher compression engines, like those that are turbocharged or supercharged, must run high octane gas, the 93 octane stuff. Why? The higher the octane level, the higher the temperature at which the gasoline burns. Therefore, you don't get compressional ignition, and therefore your engine doesn't blow up. You see, if the mixture of gasoline and air blows up before the spark plug says so, this whole connected system of connecting rods and pistons and crankshafts and valves, it gets out of timing and it will destroy itself. That's why you have a choice of gasoline. Now, if you don't have a supercharged or a turbocharged engine, really you probably don't need to run the higher octane gas. It does nothing for you. But if you do have those higher compression engines, you have to run it or your engine will knock or detonate. Okay, all of these examples, from the hairspray to the spray-on suntan lotion to the compressional engine here, the combustion engine, all has to do with the compression and expansion of a gas. So what do we need to understand? Well, in the atmosphere, we're going to be composing these parcels that rise. And as the parcel of air rises, look at these 4 bullet points. 1, as it rises, the parcel expands in size. Why? Because the air pressure around it as it goes up decreases. This allows the parcel to work on its environment, thus cooling. Well, bullet point number 2 says, well, that cooling can lead to condensation. You understand this. The cooler you make the air, the closer to saturation it will be. So if you cool off the air, you get the air closer to its dew point, which can lead to, well, in this case, cloud formation. But what's neat is when you start to make a cloud, as the water vapor condenses, it releases heat. And the heat that's released can make the thunderstorm buoyant. So in the case of a large thunderstorm, the parcel's rising, it's expanding, it's getting cooler, but a cloud is forming inside that parcel, and that releases a lot of heat, and that heat can make it several degrees warmer than its surrounding environment. And just like the hot air balloon, the parcel of air, or as you see here in this picture, the thunderstorm, is now warmer than its surrounding environment, and therefore it's buoyant and rises on its own. We learned this way back in our lectures on temperature. Warm air rises because it's less dense. Now, as that whole process happens, the atmosphere is being filled with liquid water. It was once water vapor, now it's liquid water in that thunderstorm. And it can weigh billions and billions of pounds because there's billions of gallons of water in it. But because this thunderstorm is warmer than its environment, the atmosphere can support it. So think about this. When you walk under a massive thunderstorm, that thunderstorm cloud is warmer than its surrounding environment. And you're walking underneath billions of gallons of water. But it's supported vertically in the atmosphere simply because that thunderstorm is so warm, and just like a hot air balloon, it stays buoyant. Okay, that's the tricky concept. So let's break it down. Let's go back to my video there that Adam gave me showing you the rising air. Why does this whole thing happen? Well, look at the notes. Rising air cools by expansion. We get that now. As the air rises, it gets bigger and bigger and bigger. The parcels get bigger and bigger. They work on their environment and they get cooler. If you sink the air, it warms by compression. Now, what is the temperature change and how can we calculate it? Well, from the first law of thermodynamics, we learn this number. It's a pretty interesting number. It's 10 degrees Celsius per kilometer. In Earth's atmosphere, if you take a chunk of air, a parcel, and allow it to rise, every single kilometer that it ascends, as long as it stays dry, it'll cool 10 degrees. So if I were to go outside right now and grab a chunk of air, let's say that chunk of air was 30 degrees Celsius. That's about 86 degrees Fahrenheit. If I took that chunk of air on some magic ladder, which I don't have, but if I did, and I grabbed it and carried it up 1 kilometer, 2 things would happen. 1, the parcel would expand in size. We know this, right? You ever let go of a balloon at a party? Well, the balloon eventually pops because as it goes up, it expands and pops into the low atmospheric pressure aloft. Well, that expansion leads to cooling. And if I were to climb up 1 kilometer, my parcel, which started off with a temperature of 30, would cool down to 20 degrees Celsius. We get that from the first law of thermodynamics, and it basically says this. If you have a parcel of air, that's a chunk of air, that's rising in the atmosphere, it cools 10 degrees every kilometer. If you bring it down in the atmosphere, it compressionally warms 10 degrees every kilometer. But all of this only happens if that parcel is dry, no cloud in it. You see, if we start to make a cloud in it, well, that rate decreases. Instead of cooling at the very quick rate of 10 degrees Celsius per kilometer, well, the moist adiabatic lapse rate is only 6. And this only applies to air that is rising because whenever air sinks, it compressionally warms. And if it compressionally warms, the relative humidity decreases and the cloud evaporates. We'll see that again in a few minutes. So what's the point here? A dry chunk of air as it rises cools at 10 degrees. A moist chunk of air, that's one where we're actively making a cloud, cools at 6. Basically, why is there a difference? The difference is because you get about 4 degrees of warming from condensation. So 10 degrees without it, 6 degree cooling with it. Now that's a tricky concept to get, so let's keep trying to apply this. I've got this picture of a big thunderstorm down there in the bottom right. And I'm going to launch 2 weather balloons. One weather balloon, number 1, is going to go right into the thunderstorm. It's going to be in a parcel. On the outside, I'm going to launch a weather balloon into the environment. Let's launch the balloon in the environment first. There it goes. It's ascending, and I'm tracing out over there on that diagram labeled number 2 in the bottom middle what the temperature and dew point temperature profile look like. Now notice, it's outside of the thunderstorm. Therefore, the temperature and dew point line never touch one another. But that would be the environmental temperature profile. Balloon number 1 is going to go up inside of the storm. Because it's inside of the storm, it's inside of a parcel. And because it's inside of a parcel, it only has 2 rates at which its temperature can cool. Below the cloud base, it'll cool at 10 degrees. Above the cloud base, it'll cool at 6 degrees Celsius per kilometer. Therefore, when I launch balloon number 2, look at the temperature line that's traced out over there on the left. It's very smooth. And it looks that way simply because we're cooling at 10 degrees Celsius per kilometer down here and 6 degrees Celsius per kilometer here. And cloud base is found right there where we have the switch. So below this, no cloud, and above it, cloud. Now the reason why there's not 2 lines is because if I'm in a cloud, my temperature line and dew point line are on top of one another. Down here at the bottom where they're separated, I'm below the cloud base, which is somewhere right about, well, that wasn't a very good line, somewhere right about in here, okay? All right, stick with me. This is tricky, but let's try to break this down, all right? Outside of the storm, we measured this. That's the environment. Put it on the big diagram on the bottom. Inside of the storm, we measured that. Let's put that on the diagram. Now, if you come back to the key idea, which I stressed a few moments ago, the key idea was to always compare parcel to the environment. If the temperature of the parcel is warmer than its environment, it ascends. If it's colder, it descends. And this diagram lets us assess this. This is Storm Chasing 101. When I storm chase, I look at diagrams like this to tell me if the atmosphere is capable of producing severe weather. But this is what's interesting. We actually go out and launch weather balloons twice a day, right? So we get these soundings twice a day. We don't launch them directly into thunderstorms unless we're researching those thunderstorms. Which means when we go out and launch a weather balloon, there may not be a thunderstorm there at the time we launch it. But we always want to know, is the environment capable of producing a thunderstorm? Well, there's a simple answer to that. Draw a parcel line on it. That parcel line will represent what would happen to a chunk of air if we lifted it into that atmosphere. And that's what we're trying to understand. When you're looking at this, here's the key thing to remember. That blue line is a parcel line. The black lines represent the temperature of the environment and the temperature and the dew point temperature of the environment. If the temperature of the parcel is warmer than the temperature of the environment, the atmosphere, wherever that's true, is unstable. If the temperature of the parcel is colder than the temperature of the environment, the atmosphere is stable. Unstable atmospheres produce thunderstorms. Stable ones don't. Therefore, whenever you look at these diagrams, if you see that the parcel line is the farthest right line on the sounding at any point in the atmosphere, that part of the atmosphere is unstable. If not, it is stable. Now stick with me. Let's keep getting some application here. All right, here's our picture of our thunderstorm again. 3 more questions to answer. Why do they have a flat bottom? So why is the base of the thunderstorm so flat? Why does the middle part of the thunderstorm bubble up like this? And why does the top look flat as well? So they have kind of flat top and bottom, and in the middle it bubbles quite a bit. To answer these questions, remember these 3 bullet points. Rising air cools. Cooling the air leads to condensation. That releases a lot of heat and makes the thunderstorm warmer than its surroundings. And if the parcel is warmer than its surroundings, warmer than its environment, it's buoyant. It rises. It accelerates upward away from the surface. Okay, another picture of a thunderstorm. I want you to be able to recognize 3 features, both in the real world, here on a picture of a thunderstorm, and on a sounding. The first is called the LCL, the lifting condensation level. There it is. See that gray line there? That represents cloud base. I'll take it away and put it back. See the flat bottom on that cloud? Have you often noticed that cumulus clouds or cumulonimbus clouds have flat bottoms to them? The reason why is because that was the point to which we had to lift air from the ground to where it cooled enough that it reached its dew point temperature and condensation began. So it's the point above the ground that the air has to be lifted to get condensation to form. So when you look at this, the LCL tells you everything. It's the lifting condensation level, or cloud base. Remember, as air rises, it cools. Cooling the air increases the relative humidity. At that line, the LCL, the temperature has cooled to the dew point, the relative humidity is 100%, and we begin condensing liquid water. And that's why we can see the cloud. The water vapor condenses to become liquid water. Now, we'll look at that point again in just a few moments. Let's keep going though. At some point above the LCL, the cloud base, you start to see the cloud begin to bubble. Okay? That point happens at something called the level of free convection. Now, what is this? Well, the LFC is the point above the ground that the parcel first becomes warmer than its environment. Now, think about that. If a parcel is warmer than its environment, it's buoyant. When the hot air balloon is warmer than its surroundings, it's buoyant. It rises. This is the point where we start to see the instability in the atmosphere form, and that's where the cloud begins to bubble. And it does that all the way up to the top of the storm. So the unstable part of the atmosphere, where the clouds bubble like this, is where we have rising air due to buoyancy, where the parcel is warmer than its environment. So we have to mark that point. Where does this happen on the sounding? We got to find that bottom point. And we're going to find that in a few minutes. Finally, I want to show you this. As that air rises, it eventually slams into the very stable layers at the top of the atmosphere. So the air goes up and spreads out horizontally. We call that layer, that level I should say, the equilibrium level. It's the point where the anvil cloud forms, and the anvil cloud is this big cloud you see over here. We'll talk about that quite a bit this semester. It's where the air parcel hits the very stable and warm layer in the stratosphere and spreads out horizontally. You see, it can't continue to fly into the stratosphere. The air can't, because the stratosphere is warm. It's like you taking a hot air balloon ride into hot air. The balloon won't be buoyant in that situation. It has to be cold around the balloon. Well, the equilibrium level marks the top of the thunderstorm. Okay, this is a really good example of all of it put together. A picture taken by the International Space Station. And you see this cloud here? That is the anvil cloud sitting on top of the thunderstorm. The thunderstorm's main updraft is underneath, like this. This is the unstable part. But it slams into the stable stratosphere and spreads out horizontally. By the way, the bigger these anvil clouds are that I'm shading here, the badder the thunderstorm is underneath it. Well, let's keep going forward. Let's get some real practice with this, okay? I have got here a sounding. The black line on the right, that is the temperature line. The thick black line on the left, that's the dew point temperature line. And the thin gray line is the parcel line. Now, we'll get them labeled here for you, okay? Remember our goal. Let's try to find any locations where the parcel is warmer than its environment. Where that begins is if you start from the bottom, which is down here, and work your way up. Look, the very first point where the parcel is the farthest right line is right here. That's the level of free convection. You see right here, the parcel becomes warmer than its environment. Remember, temperature increases in this direction in the sounding. So the thin gray line is the farthest right line. It's warmer than its environment. So at this point, right in through here, is where our thunderstorm begins to bubble. But that's not the bottom of it. We'll talk about that in a few moments. This cloud will continue to rise until it hits its equilibrium level. And that's where the parcel then again becomes cooler than its surroundings. So basically, between these two yellow arrows, which I just drew here, the atmosphere is unstable. Below and above that, it is stable. But this is why the troposphere gets its name. Tropos means overturning. So that's the part of the atmosphere that allows for overturning, which basically means we make thunderstorms. Cloud base, though, is way down here. And what you can see is the parcel is cooling at a rate like this, and there's a small kink right here where it starts cooling at a lesser rate. In fact, all parcel lines, if you just allow me to draw over here on this side, all parcel lines look like this. They have a very distinct break right there where the parcel stops cooling at the dry rate, which I'll label with a D, and starts cooling at the moist adiabatic lapse rate, which I'll label with an M. That point, which I've highlighted with the arrow, is cloud base. Okay, that's cloud base. We'll come back to this idea a few times to make sure that it sits pretty well in your brain. Now, once we see cloud base, we're going to calculate something called the lifted index. You know how we often like to explain the motion of the stock market by looking at indices like the Dow Jones Industrial Index or the S&P 500 Index? Well, just like with those indices, we like to look at atmospheric indices. I'm going to teach you about two of them. The first one is called the lifted index. and it's a very simple calculation. It's done midway up in the atmosphere at 500 millibars, and it's always calculated there. And it's a difference between the temperature at 500 millibars, which is right here, and the parcel temperature at 500 millibars, which is right there. Just read off the sounding all the way at the bottom down here what the temperature of the environment is. Let's call that minus 26. The parcel is here. We just go straight down to the bottom and read off its temperature. We've got a little squiggly there, but you see, we'll call that minus 23. Well, minus 26 minus negative 23 is negative 3. And all that means is, right here at 500 millibars, the parcel's 3 degrees warmer than its environment, and therefore buoyant, just like the hot air balloon. So it's a quick and dirty assessment. Here's what you need to remember. If the lifted index is negative, that's a good environment for thunderstorms. Positive, not so good. The last thing I want you to see here is I just shaded in this area here yellow. You see, when we design these thermodynamic diagrams, the sounding diagram you're looking at the background, area on these diagrams represents energy. And therefore, the more of this positive area between the equilibrium level and the LFC, the more unstable the atmosphere is and the more supportive it is of massive thunderstorms. We call that CAPE, like Superman's cape. But CAPE here is an acronym. It stands for Convective Available Potential Energy. So it's the potential energy of the atmosphere. All right, with all of that, when this all comes together, you build a massive thunderstorm like this one. It has a well-defined cloud base. It has a part where the thunderstorm starts to bubble here at the LFC and a big flat anvil cloud on top at the equilibrium level. Now, pause the video, go back and re-watch that if it wasn't 100% clear. But what I'm going to do is I'm going to press forward and show you some examples. We have two soundings. These are real live soundings. On the left-hand side, Lincoln, Illinois, which is in the center part of Illinois, November 17, 2008. I've got the temperature of the environment. That would be this line. Whoops, sorry about that. That would be this line right here, okay? I have the temperature, the dew point temperature of the environment. That's this line here. And this line, which I just labeled, I'll label it with a P here. That's the parcel line. Now, we just learned about this index called the lifted index. And remember, it's the environmental temperature minus the parcel temperature. Well, let's see what happened on November 17, 2008. Well, let's just find what the environmental temperature is. It's right there. There's the parcel temperature, which is here. So I've kind of put blue circles around them. Read off the bottom. 24 degrees, minus 24, is my environmental temperature. Subtract from that my parcel temperature, which is negative 43. See it down here? That gives me a lifted index of 19. On this day, with a lifted index of 19, it was a crystal clear, blue skied, beautiful fall day. Nothing going on. You see, when the lifted index gets negative, that's when the atmosphere gets unstable and you increase the probability of having nasty weather. Positive lifted index values, no thunderstorms. Negative, that's when we get thunderstorms. So let's take a look at that example. Go over to the sounding that's on the right. This was on the 5th of August, 2008. Look at your parcel line. That would be the blue dashed line that you see right here. Okay? The temperature of the environment, that's this line in here. And the dew point of the environment is right here. All right, here we go. What was the lifted index? Well, at 500 millibars, there's my temperature of the parcel. Here's my temperature of the environment. Read them off the bottom. Subtract -8 minus 5. That gives me a lifted index of -13. That means that the parcel is 13 degrees warmer than its surroundings, its environment here at 500 millibars. Look at the chart. Anything less than -6 is extremely unstable, severe thunderstorms probable, tornadoes possible. I will never ever forget this day because not only was the lifted index so low, but we had an enormous amount of CAPE. Remember, that's the positive area between the parcel and its environment. Now, what does that mean? Well, on that day, CAPE values hit 7,000, and here's the unit, joules per kilogram. Now, don't worry about that unit too much. I just want you to hear this. When we make massive supercells that produce big-time tornadoes, strong straight-line winds, hail, everything, Research shows that generally if you have anything over about 1,000 or 1,500 joules per kilogram of CAPE, your atmosphere is primed and ready to rock and roll. So when I saw 7,000 as the CAPE value, that was a pretty amazing day back in August of 2008. By the way, over there on the left-hand side, that sounding, the lifted index was positive, boring weather, and no CAPE. There is no CAPE, because not once does the parcel, that's the blue dashed line, get warmer than its environment. You can't have CAPE in that situation. Well, let me show you what happened on the day here, on the night actually of August 4th, because remember, 0Z on August 5th is 7 p.m. on August 4th, local time here in Champaign. Well, this is what happened. There was a Cubs-Astros game, and in the middle of that Astros game, there were tornado sirens that went off because this nasty complex of thunderstorms produced 5 tornadoes in Chicago. 5 tornadoes. Look over here at this satellite animation. Do you see this big blob of clouds? That is the anvil cloud. We're looking down from above. That's the anvil cloud sitting on top of this. And when these storms reached Chicago, I was down here in Champaign, Illinois. I could take pictures of that anvil from Champaign, even though the storms were in Chicago. Absolutely amazing severe weather day, given that we had 7,000 joules per kilogram of CAPE and a negative 13 lifted index. Amazing to see that. All right, let me take you up a level here to kind of my nerd level here in atmospheric sciences. We often look at a little bit different type of sounding than what I just showed you. The type you look at is called a Stuve diagram, which is the one you're always going to see in my class. But I want to show you briefly what a skew T log P diagram looks like. See the diagram down there at the bottom? Well, there's the parcel line. There's all the CAPE. The lifted index on this particular day, minus 8.55 with a CAPE value of 3,135 joules. So our lifted index was negative, our CAPE values were high. Look at the instability in the atmosphere. And by the way, watch me draw here, right here, whoops, a little bit high there. Right here is the LFC. Right there is the equilibrium level. And right down here, do you see where the blue line makes a sharp turn? That's cloud base. On that day, this massive wedge tornado formed in Oklahoma. And it's quite famous. It's the May 20th Moore, Oklahoma EF5 ranked tornado. That's right, wind speeds over 205 miles an hour. And look at how complete the destruction was. You see, this is why we spend so much time trying to understand stability. Without it, we can't produce stuff like this. All right, let's get some practice. I've got a sounding over there on the right-hand side. Okay, you see it. Here's my first question. What is the pressure at the LCL? The pressure at the LCL. Now, LCL, remember, stands for lifting condensation level. LCL. It's also synonymous with cloud base. As a hint, remember all parcel lines look like this. And this little kink right in through there is the LCL. Down here, the parcel's cooling at the dry rate. Here, it's cooling at the moist, which means cloud base is right there at that level. Well, look at the sounding, see if you can find it. I'm going to help you. It is right in here. Okay? Whoops. Right there. Do you see how the blue dashed line, which is a parcel line, is cooling at the 10-degree rate, and right here switches to cool at a slower rate? That's where the LCL is, and that would be 900 millibars. Now, how do I know that? Well, that point is here. I just read across, and I see that it's at 900 millibars. My next question for you. What's the pressure of the LFC, the level of free convection? LFC, remember, that's the first point when you start from the ground looking up, where the parcel is warmer than its environment. It's the crisscross point at the bottom, and I see it right there, and that is roughly 750 millibars. Okay? Next, so we've canceled out 750 millibars, we canceled out 900 millibars. My next question for you is this one. What's the pressure at the equilibrium level? Well, at the equilibrium level, remember that's where they crisscross again, and that's way up here. So at that level, let's call that, well, about 150. Here's 200. That's 175. So that is 175 millibars. So that's how we do it. 3 points to identify. The bottom one, the kink, that is the cloud base, LCL. Where they crisscross the first time at the bottom, LFC. Where they crisscross again at the top, EL, or the equilibrium level. My last question for you is this. What's the value of the lifted index? Let me erase some of this so we can see a little bit better. Well, what's the value of the lifted index? Well, as I look at this, let's go to 500 millibars. That's where we calculate it. And go across. Here's the temperature of the environment. Here's the temperature of the parcel. Now, the environmental temperature, if I just kind of bring this down, straight down here, is somewhere right in through that area. We'll call that minus, I don't know, minus 18. We'll start with the parcel and come straight down. Sorry, it's hard for me to draw. We'll go right there. We can call that about minus 13. So minus 18 and minus 13. So minus 18 minus negative 13, negative 5. Is this environment supportive of making a thunderstorm? Yes. Why? The lifted index is negative. And all this in here, all of that is CAPE, convective available potential energy. Sorry, I can't draw very well on this. This is all CAPE, all of this and stuff in here. This is storm chasing 101. Without the instability, we can't make our thunderstorms. Okay, with that, let's press on to the next thing. Here's a few questions to get us ready for the next part of this lecture. Make sure we understand this. Okay? True or false? The atmosphere is said to be unstable if the parcel's temperature is warmer than the surrounding environmental temperature. Well, the answer to that is yes, absolutely true. It's unstable if the parcel is warmer than its environment, just like the hot air balloon. Another question. True or false? A negative lifted index indicates an unstable atmosphere. What do you think? Well, hopefully you remember this, and that this is also a true statement. A negative lifted index does indicate an unstable atmosphere, one that can produce lots of thunderstorms. Here's another one. The stratosphere is defined by a large temperature inversion. Is the stratosphere a stable or unstable layer in the atmosphere? Well, remember that unstable layers are ones where the parcel can be warmer than its environment. In this case, if the environment is warm, it's hard for the parcel to get warmer than it. So the stratosphere is a stable layer, and that's why it acts as a lid on all of Earth's weather systems. Imagine what would happen if the stratosphere didn't exist. Our thunderstorms could potentially be 30, 50, 100 miles tall, but thankfully because we have a stratosphere, that doesn't occur. The stratosphere caps it all. And my last question is this one. Which body of water is the primary moisture source for thunderstorms in the Midwest? The Midwest composes of states like Illinois. In other words, where does all the moisture come from that's in our thunderstorms? Well, is it the Pacific Ocean, the Atlantic, the Great Lakes? Is it the Gulf of Mexico, or is it groundwater in the aquifers that are underneath Illinois? Well, the answer to this one might surprise you. Even though our weather comes from the west, it all gets blocked by the moisture all gets blocked by the Rocky Mountains. The Atlantic Ocean, well, that's to our east, and it's rare that our weather comes from the east, but we can routinely get winds out of the south. And as a consequence, our moisture source is the Gulf of Mexico. The Great Lakes can add moisture, but they're relatively too small. And the Muhammad Aquifer, well, that water that's in the aquifer is way below the Earth's surface, and as a consequence, it's not getting into the atmosphere. Our primary moisture source is the Gulf of Mexico. All right. Our last three ingredients are going to go a lot quicker than the first one. What does it take to get a thunderstorm to form? Well, if the atmosphere is unstable, you got to have something that can lift the air into that unstable part. So this animation here of bubbling thunderstorms in the afternoon, well, something had to trigger the air to rise into that. And a trigger mechanism, which is ingredient number 2, also called the lifting mechanism, is anything that can cause the air to rise. Let me give you a few examples of this, okay? Let's talk about fronts. Here's a satellite image looking down on Nebraska and Kansas in the center part of the United States. What's going on here is we have this big dry plume of air coming out of the desert like this, coming off the mountains out of the desert. And that air is racing forward just like this. On the other side, I have this big plume of humid air coming up out of the Gulf of Mexico. And these two air masses collide right here. See it? They bump into one another. And when the air collides at the surface, it can't go anywhere else but up. Well, if the atmosphere above it is unstable, look at the thunderstorms that erupted because of this. On this day, 57 supercell thunderstorms blew up right on that boundary, that front that caused the air to rise. It caused it again by converging air near the surface, causing it to go up. Incredible to see that. Let me show you what a front looks like from a cross-sectional view. So I got this box. We'll say to the north is to the left and to the south is to the right. Well, oftentimes we get these big pushes of cold air that come out of Canada like this. And that cold, dense air kind of acts as a ramp. It's a ramp for the warm, moist air to run right up over the top of the cold front, because warm, moist air is less dense than cold, dry air. So the warm, moist air hits it, goes over the top, and as it rises, it expands. As it expands, it cools. As it cools, you get condensation. Condensation makes clouds. And guess what? Those clouds rain and produce a lot of lightning and thunder. The cold front served as the trigger to get the air to rise. Let's look at some examples here. I got a top-down view and a side view here. The arrows tell you which way the wind was blowing. I had wind coming from this direction on one side, this direction on the other. And it collided right there in the middle. And the air rose and made a series of thunderstorms. So this is again an example of triggering the air, causing it to rise. Let's get another example here. This is a pretty awesome view here of some clouds forming on a mountain. The air is actually being forced to come up the mountain like this. And as it rises over the mountain, well, it's cooling. And the cooling effect leads to condensation. And the condensation makes clouds. Now you can clearly see that this particular example, the atmosphere is not unstable. That's because the clouds are not bubbling up and rising rapidly above it. They're only forming where the mountain is forcing them to rise. But still, orographic lift or lift over the mountains can make this happen. Let me show you an example. June 16, 2018, watch the thunderstorms rapidly develop right here over the Intermountain West. See them all? These are all thunderstorms, big ones, blowing up here on the mountains. The mountains are the trigger. They force the air to rise. And also the mountains help heat the air. It's because the sun beats down on their rocky slopes, getting it really hot, and the atmosphere just pops when this happens. Rapidly ascending air in an unstable environment. Our mountains get lots and lots and lots of thunderstorms here in the United States. Okay, let's go to another one. Check out this video. I want to show you something. You see, I told you about what happens when air goes over the mountain on one side, but what happens if it descends on the backside? Well, whenever that occurs, descending air compressionally warms and clouds evaporate. So that's what you're seeing here. Pretty neat to see that. Let's keep going. What about the sea breeze? You see, the southern tip of Florida gets thunderstorms, actually almost the entirety of Florida, including the entire, both Panhandle and Peninsula, have lots and lots of thunderstorms because every day during their warmer time periods, which is pretty much the whole year, they have this breeze that comes in off the shore. It converges right when it hits the land and triggers the air to rise, just like that, making huge thunderstorms. This is why Florida is not only the thunderstorm capital of the United States, but the lightning capital of the U.S. They get thunderstorms all the time. Now, how do these work? Well, on the top, I have a top-down view, and on the bottom, I have a cross-sectional view. You see, in the middle of the afternoon, especially in the summer, the peninsula gets hot. The surrounding waters are relatively cool. Well, the atmosphere responds by creating a wind, because where there's cooler air, higher pressure, and hotter over the land, lower pressure. And the air converges once it makes contact with the land. And as it slows down because the friction there, the air is forced to rise. It makes thunderstorms just like this. You see, that's why the sea breeze can kick off such amazing thunderstorm activity. Now, let me give you another one here. Sometimes, just because of solar heating, the sun beating down on the ground, you can get some pockets of the ground to just get hot. And they get so hot that the air starts to rise there and bubble up. And that's the animation you just watched. This was again on June 18th. We had all three of these animations around June 18th, 2018. The atmosphere just bubbling away. All of a sudden, it just gets nice and hot. We trigger a rising thermal, and it goes up and makes a thunderstorm. We call these ordinary thunderstorms, and they're amazing to watch. In fact, my most favorite thing about this animation is all the way at the end. Check this out. At the very end of this animation, right in through here, look. As the sun is setting, look at it casts these long shadows off the tops of these thunderstorms. If that just isn't the coolest thing, I don't know what else is. That's amazing to look at. All right, one last thing about rising air. Turns out when volcanoes erupt or when we have huge fires that break out in our forests, we can actually use the heat from the fire to cause the air to rise, creating what's called a pyrocumulus cloud. And that's what you're looking at right here. Amazing to see that. Smoke down here, cloud on top. Pyrocumulus, heat from the fire causing the air to rise. All right, let's get into our last two ingredients. Here we go. We now know that we need an unstable atmosphere, ingredient number 1. 2, a trigger. But 3, if that air is dry, it doesn't matter. We've got to have an abundant amount of moisture. Now, why is that? Well, the ultimate energy source for making the cloud buoyant so it can carry all those billions of gallons of rainwater is it's got to have a lot of heat in it. And the heat comes from condensation. And the condensation comes from really, really humid air at the surface. When I storm chase, I do not storm chase unless the dew point temperatures are over 60 degrees Fahrenheit. And I want you to look at this map that's in the upper right here. I just put a line on top of it. That line follows the contour of the 60-degree isodrosotherm. That's just a name for a line of constant dew point. Everywhere that you get on this side of the line, the dew point temperatures are above 60. And that means the atmosphere is juicy, it's ripe, it's full of moisture. And on this day, do you notice this? It's this little pocket in here of really high dew point temperature. Well, yes, most of our moisture comes out of the Gulf of Mexico, just like this. But we can have a second supplement to that moisture right in through there. The reason why there was such high dew points here, higher than anywhere else, is because of corn and soybeans. You see, the two primary sources for our moisture are the Gulf of Mexico and evapotranspiration. That's where water is evaporated out of the soil and vegetation. So the Gulf of Mexico advects the moisture north. This is everywhere east of the Rocky Mountains. And the plants can help evaporate, putting more water into the atmosphere. By the way, they can put as much as 3,000 to 4,000 gallons of water into the air per acre of corn every day. That's a lot of moisture. We call it corn sweat, and it can really bring up the humidity levels. Okay, so we've got the Gulf of Mexico giving us the moisture. We also have the evaporation off of vegetation giving us moisture. We have a trigger mechanism like a cold front lifting the air, or mountains lifting the air, or a hot spot, a warm spot lifting the air. We need to do all of that into an unstable atmosphere. You get all that to happen, you'll make a beautiful thunderstorm like this one. Jessica Moore let me use this picture. It's a brilliant, beautiful, breathtaking picture of a massive thunderstorm in Montana. And look, see the flat bottom? There's the LCL. See it bubbling in the middle? That's where the LFC is. See the big anvil cloud spreading out on top? Well, that's when it hits the equilibrium level. It's all right there. You get 3 ingredients coming together, an unstable atmosphere, a trigger mechanism, and moisture, you'll make one of these, all right? And boy, I think I got to take my drawings off because I'm ruining it. What a beautiful picture that Jessica gave us. Now, ordinary thunderstorms work just like this. They're composed of an updraft. What's an updraft? Well, just warm, moist air that's rising. We know that as warm, moist air rises, it cools. That gives you condensation. That makes clouds. As that updraft rises, it can extend through the entire depth of the troposphere. You see the top, where the anvil cloud forms, typically sits at the base of the stratosphere, where the tropopause is located. And every thunderstorm produces one of these. Every thunderstorm produces an anvil cloud. You see, when a thunderstorm is composed of just an updraft, it's usually not precipitating. But once it reaches its mature stage, it develops a downdraft. And the downdraft is this. You see, we tend to mix in a little bit of dry air from the outside, which causes some evaporation, but we're basically filling the air with precipitation-sized particles, raindrops. And as they fall, they drag the air downward, and as they fall, we get some evaporation, which gives us this very cold, dense pocket of rapidly descending air that's full of precipitation. That's the downdraft. That's, by the way, what the radar is designed to see. You see, the radar scans for precipitation. Wherever you see it, you're in the downdraft of the storm. But you see, my bullet point at the top there says ordinary thunderstorms are rarely severe. They rarely last more than about an hour. And the big problem is this: gravity. You see, what goes up must come down. And in this particular case over here, the updraft, which is here, is too close to the downdraft, which is there, and they can cancel one another out. And if the updraft is not separated from the downdraft, sorry about that, if the updraft's not separated from the downdraft, well, you won't make a thunderstorm that can last long enough to become severe. So here we go. Our final ingredient takes an ordinary thunderstorm, which uses an unstable atmosphere, a trigger mechanism, and a lot of moisture. Well, it takes it to the severe limits. First, let me show you what these updrafts look like. Here's a big updraft billowing in the afternoon. When we put it in a time lapse, look at how rapidly the air ascends. Sometimes in these updrafts, which are just triggered parcels of air rising into the atmosphere, we can get updraft speeds over 100 miles an hour. Impressive to see that. But like I said, what goes up comes right back down. The National Weather Service gave me this video. You're about to see a microburst. Here it comes. Boom, there it is. That's a rapidly descending pocket of precipitation-loaded air. That's the downdraft. And in this case, this downdraft is violently descending at speeds well over 100 miles an hour, causing straight-line wind damage. Watch it again from out right here. There it is. See the pocket of air descending? This is the rain falling out of the back of this storm. So updrafts and downdrafts. By the way, a telltale sign that the downdraft is powerful, well, here's the rain shaft coming down like this. But do you see how, right here in the edge, it kind of bows outward like that? That footprint of the downdraft is because it's slamming into the ground and having to spread out horizontally. And as that happens, it can produce incredibly strong straight line winds, winds that can exceed 100 miles an hour. So look for that shape when you see the downdraft or the thunderstorm. And this is what we're looking at right here. This is the descending air in the downdraft of this storm slamming into the ground. Beautiful picture from the National Weather Service out of Phoenix. So here's where we finish this long lecture. You got your first three ingredients. The atmosphere is unstable. We have plenty of moisture in a trigger mechanism. You want it to become severe? Add in wind shear. You see, wind shear is a change of wind speed and direction with height. Write that down with me, okay? It's a change of wind speed and direction with height. And wind shear will separate the updraft from the downdraft. Remember, when they're not separated, what goes up comes back down. Where do we look for wind shear? On our soundings, okay? Look at the right-hand side. We've learned how to read the winds on soundings. This is how we get it. Let me show you an example here. I got a little diagram up here at the top that shows you what an environment looks like with no wind shear. See how the length of these arrows representing the wind don't change with height? There's no wind shear. When that happens, thunderstorms do this. They develop vertically. See it? See, there's the rapidly rising updraft. But the problem is there's no wind shear. Nothing's pushing that updraft downstream. It's just going up. Boy, it's beautiful. Rising turrets of parcels of air accelerating upward in the destabilized atmosphere. Okay? But watch this. What goes up must come right back down. And in this case, the downdraft of this thunderstorm is killing the updraft. The storm is killing itself. That's not played in reverse. That's an updraft collapsing on its downdraft. Wind shear, though, is when we start to add an increasing wind speed with height, or changing the direction of the wind with height. You see, wind shear like this makes thunderstorms powerful. Here's another time-lapse video, but in this case, the winds are getting faster with height. Do you see how it's blowing the top of the storm off? Look at this. See how it's going this direction? Well, the downdraft then falls over here, not back through the updraft, which is over here. See, there it goes up and down over there. Whereas in the previous time-lapse video, this thunderstorm was dead after about this long. This one is healthy and surviving, and new updrafts form on the backside, allowing the storm to continue to get stronger and stronger and stronger. Here's the other thing we're about to learn. When we have wind shear, storms can also spin, and that gives rise to the development of tornadoes. All of these topics, now that we've started learning some of the basics here of Storm Chasing 101, finding your four ingredients, an unstable atmosphere, a trigger mechanism, plenty of surface moisture and wind shear, well, all of these things come together to make the most powerful expressions of weather on Earth, thunderstorms. And now we've got it down. These are the basics we have to understand as we move forward with our lectures on severe weather.